Okay. All right, I apologize. My Wi-Fi got shut off by one of my kiddos. Little stinkers. All right. All right, so again, I was saying if we converted NH3 to its conjugate base, it would be NH2 minus, right?
Yeah.
Okay, let's do the same thing for H2O. So if one of the protons was to be taken, it would be OH minus. And then again with H2S, we'd have SH minus. Okay, so now we're going to want to compare the stability of each of these. Okay, which atom, nitrogen, oxygen, or sulfur, holds the negative charge best? In other words, which one is most electronegative?
Oxygen.
Yeah, right. Oxygen. So our most acidic now is going to be our H2O. Does that make sense? Because it's the most stable base.
Okay.
Okay. All right, so now we want to compare nitrogen and sulfur. Which one is going to be? Oh, wow. It doesn't even show as H2O is our most acidic. Let's see.
Yeah, that's what I was. So, like from
Is the
other.
answer A?
Yeah.
Interesting. It must be that sulfur is bigger than oxygen.
Yeah, that's what I was actually like. That was the only answer that I could match with A, like the size.
Right.
Because it says acidity increases with the size too.
Yeah, that is true, but I would have thought oxygen, I guess because there's probably so comparative in electronegativity, sulfur and oxygen, that must just make the difference. Okay, so I guess just remember that one for the exam, right? So sulfur and oxygen are comparable in electronegativity, and so the size will make the difference here, and then NH3 will be your weakest. Does that make sense?
Yeah, so like I was wondering when there is like electronegative and size together, like will the size win the electronegativity or?
Yeah,
like...
I've actually never seen him test on one that close. Okay. Usually it'll be like, you know, fluorine, and then I guess, well, yeah, because he has tested on like the difference between like chlorine and bromine, which chlorine is technically more electronegative, but bromine is better at holding the negative charge. Yeah. So yeah, I would just definitely know that when they're that comparable as far as electronegativity goes, if they're right next to each other, then I would compare size over electronegativity.
All right. All right.
I apologize for my misunderstanding there.
Very good. And next question was this. So the answer was D, but
the answer is A, you said?
D.
D?
Yeah.
Okay. All right, well, he actually doesn't focus on Bronsted acid or Lewis acid bases much. Right. But as far as my understanding goes, basically what you want to look for is, well, I'm trying to remember for sure myself. It's been a while since I reviewed these.
We can skip this question if it is not really.
Yeah, I want to learn myself as well. So I want to make sure you guys are prepared if he does ask a question on it. So I'm just Googling really quick. I'm sorry. Okay, so for Bronsted-Lowry, I do remember this now, the acid is the proton. Okay, so the acid is one that gives up a proton, and the base is the one that accepts the proton. Okay, whereas a Lewis acid is an electron acceptor. So Bronsted-Lowry has to do with hydrogens being moved around, whereas Lewis acids and bases have to do with electrons being moved around. Does that make sense?
Yeah.
So for example, on this one, for number 1, well, let's talk about number 2 here, because that'll be easier to determine, right? So because there's no protons being moved around, because there's only aluminum and chlorine, right? So that's going to be Lewis. Whereas this one, okay, this carbon lost a proton, okay, and so now it's, you know, it's going to be, it could be both a Lewis acid or a Bronsted-Lowry acid, okay. And then this one, I'm not sure why that one would be neither. Let me think. CCl4. I'm going to take a picture of this one and I'm going to email about it and then I'll send it out to you. Okay. Because although he doesn't focus on it too much on the exams, if there was a question, I wouldn't want you to miss it. So I'm going to email him that one. Okay.
And for this part.
Okay. Perfect. So the conjugate acid of this molecule, all you do to make a conjugate acid of something is to add a proton and then determine its charge. Okay. So all you're going to do here is, right, it's, you got your CH3, CH2, and H, and then it looks like they added the proton here. So NH2, CH3. And because of the added proton, that makes it a positive charge.
Yeah.
Okay, so that's the only kind of trick there, is to say, if you're trying to make a conjugate acid, add a proton, change the charge by +1, whether it's negatively charged now and then it becomes neutral, or it's neutral now and it becomes positive. Whichever way you look at it, whatever the problem asks for, you're just going to add a proton and make it one more positive.
Yeah, but I was wondering, like, the reason the hydrogen is added to the nitrogen is because it forms hydrogen, which is more stronger bond, is it?
Yeah, that's probably a way to look at it. The other thing is it doesn't break its octet by accepting a hydrogen, whereas the carbons, if you look at this carbon chain, right, we have a CH3, CH2, and then an NCH3. This is our molecule, right?
Yeah.
And in our original, it only had one hydrogen and a lone pair. Okay. What happens now is when it accepts the proton, it uses those electrons and forms a new hydrogen bond. Okay. Whereas you couldn't slap another hydrogen on any of these carbons. Okay. That would break its octet. Whereas the nitrogen is able to receive that proton. Does that make sense?
Yeah.
Alright, what's your question on this one?
Oh, so this will be the same thing, I think.
Yeah.
So it's because of the octet rule.
Yep. So the oxygen is able to accept that proton, basically.
All right.
Yep.
And so for conjugate base, this is also gonna be octet. So okay.
Yeah. So here, I mean, you can kind of see this proton hanging out. Okay. And so when you make a conjugate base, you're going to want to just remove a proton, which he'll usually make it pretty obvious which one you want to remove. Okay. And then obviously the proton leaves and it becomes one more negative.
All right. Yeah. And I actually also tried to do like chapter 3, but there were no answer keys to that. Like, yeah. So
there's no answer keys to the practice problems.
Yeah, for chapter 3.
Oh, okay.
And also there were no there were uh, there were nothing on chapter 4, and there was only answer keys to it. So I think, will this be the chapter 3 or something?
Let's see.
Yeah.
I'm not sure. I don't have anything to do with files he adds or anything like
Yeah.
that, but I can go. Well, let me see. So let me just write down question 1 is B, 2 is C, 3 is C, 4 is A. Okay, let's go through questions 1 through 4 on chapter 3 and see if that's the answer key here.
All right.
So it said question 1 is B, identify the functional groups of the molecule shown right. Okay. We have an aromatic ring. We have an ester. We have an amine. Okay. Aromatic ring, ester, amine. Yeah, so it's going to be either D or E. I'm not sure why he has those are the exact same answer, but it's not B. There's no ketone.
I think it's D.
Yeah, I'd say D or E. They're both the same answer, but
Oh yeah. Oh yeah. Oh
so,
no, one is ether and one is ester, right?
oh yeah, you're right. I'm sorry, I wasn't reading that right. So yeah, it is an ester, so it would be D. So it doesn't look like the answer key for 4 is the answers for 3. So it looks like he just didn't upload the answer key for 3 and the problems for 4. That'd be a good email, a question you could email him. Just say, hey, I didn't see the answer key for chapter 3 or the problems for number 4. To get those uploaded.
I just have a quick one more question about this.
Go for it.
This part, the melting point. And like the questions that I have seen related to melting points was like the same compound, like not different elements added to it. So I just wanted to make sure.
Yeah. So for melting point, it has everything to do with the intermolecular forces and how strong those intermolecular forces are. Okay. So for CH3F, basically you've got, right? So you've got the most electronegative atom bonded to a methyl group, right? Same with CH3Cl. Okay, it's also very electronegative, but not as electronegative as fluorine. CH3I, okay, this is going to be our biggest molecule, but it's going to be our lowest melting point because it's not as electronegative. Okay, so our CH3F, it's not only the most electronegative, but it can also hydrogen bond. Okay.
Oh yeah.
So our highest is going to be the CH3F. Okay. And then due to the strength of the electronegativity, our CH3Cl will be next, and then CH3Ci. You okay with that?
Yeah. So we're looking at electronegativity.
Yeah. It has to mostly do with the intermolecular forces. Okay. And because all of these have basically the same intermolecular forces, they've all got van der Waals, they've all got dipole-dipole, okay? And then fluorine can hydrogen bond, that makes it our strongest. And then the largest dipole is the chlorine over iodine. Does that make sense?
Yeah.
So we're actually not looking at electronegativity specifically. That was just this example. But what you'd want to do for all melting point problems is look at your intermolecular forces. Okay, so we have van der Waals here, we have dipole-dipole, and H bonding. So that's going to be your highest melting point. Here we have van der Waals and dipole-dipole. Van der Waals, dipole-dipole. Okay, so we know this is our number 1. And then we have to look at which dipole is stronger. And we know that chlorine is more electronegative, and so this one's going to be our number 2. Does that answer your question?
Yeah.
Perfect.
So even the boiling point, it has to do with intermolecular forces.
Yeah, boiling point and melting point.
I think that's it for me. Yeah.
Perfect.
Yeah.
Delaney, any specific questions you have, or would you guys like to go over the ones I had prepared for you just in case no one came with questions?
Yeah, I was just hopping on here just to get some extra review. I didn't have any certain questions, so if you just want to go over what you have.
All right, let's do it.
Perfect.
So this is mostly, oh, go ahead.
No, sorry, we just haven't reviewed the chapter 2 through 4 since he just added that to the exam.
Mm-hmm.
So, not that I'm too worried about it, but I would definitely like to review it a little bit.
So that's what I focused on with my questions. I reviewed heavily chapters 1 and 2 in my exam review on Monday.
Yeah.
And there was actually, I realized I did have chapters 3 and 4 in there as well. Chapters 3 and 4 are basically over your naming, like IUPAC naming, and also your Newman projections and things like that. So I did have some of that in there, but we'll go over some more chapter 3 and 4 stuff together. Is that okay with you guys?
Yeah.
Perfect. All right, so I started today here with this problem. Okay, I said, how are the following related? So what we did is we converted A, B, C, and D into their skeletal structures, and then we compared what they looked like. So A and D are constitutional isomers because they have different connectivity, but they have the same molecular formula, right? Here, the methyl group is on carbon 3, whereas here it's on carbon 4. So that's how you know something is a constitutional isomer, is if they have the same molecular formula, but their connectivity is different. The same goes for A and B, they're constitutional isomers, and B and C and D. Okay, those are all constitutional isomers of each other. You can look fairly clearly, A and C are identical. Okay, and then stereoisomers are B and D. So they have the same molecular formula, they have the same connectivity, but this one has its methyl group facing up. This one has its methyl group facing down. And so that's the difference there. That makes a stereoisomer. So they have the same molecular formula, same connectivity, but their stereochemistry is different. That makes them stereoisomers. Does that make sense? We okay there, both of you?
Yeah.
So we went over that briefly earlier, but I just wanted to, in case I can't put the videos together, that was what we covered before we cut out. So, all right, convert the following to the most stable chair conformation. Okay. So I'm going to do this first one with you guys, and then I'll let you work on it, work on the rest of them, try it by yourself. Okay. So what you're going to want to do for this first one is draw a chair conformation. Okay. Then we can number, it doesn't really matter how we number as long as we remain consistent. Okay. So at carbon 1, we have a methyl group facing up. Okay. At carbon 4, which 3, 4 is this carbon right here, we have an ethyl group facing down. You guys see how we kind of work through these problems?
Yeah.
Okay. Would this be our most stable chair conformation?
No.
No, because it's axial.
Perfect. Yep. So we want to do a flip. Okay. So it would face like this. Again, this is now carbon 1 facing down, 2, 3, 4 is facing up, 5, 6. Okay. All right, so this was axial up, right? And this one was axial down. Up and down stay the same, and our axial and equatorial change. So at carbon 1, it was up, so we need to keep it up, which means it's going to go out this way. Now it's equatorial up. You guys see how that works?
Mm-hmm.
Same with carbon 4, it needs to remain down. Okay, so it's going to be something like that. It is now equatorial down. Okay, and this is our more stable.
I have a quick question.
Yeah.
Like at carbon number 4, it seems like it's up, isn't it?
Yep. So
Yeah.
how I like to look at these, let me turn on my camera.
Yeah.
Okay. All right, so how I like to look at these is at carbon 4, the bonds meet facing up, right? And so how I like to look at these is I say if the carbons meet facing up, the up direction is going to be more obvious. So if we were to have the methyl or the ethyl group facing up, it would be directly upward. Does that make sense? Because the carbons meet up, the up position is going to be straight up. Whereas if the carbons meet down, like at carbon 1, okay, they meet facing downward, the down position is going to be more obvious. It's going to be directly down. Okay, and then you kind of get the hang of how these look, but on these, any of them that kind of like at number 4, right? The up is more obvious, so the down is going to be a little bit less obvious, but as long as you draw it, I mean, we could draw it going this way, right? It would be the same thing, okay? As long as it's kind of faced outward and not up, okay? That's how he's going to make you tell the difference. Obviously, you're not going to be drawing on the exam. What's up?
Why do you still have that one? It's supposed to be up, correct?
It is. It's supposed to be down at 4.
Oh.
Because here it was axial down. Now it becomes equatorial down.
Oh, shoot. Okay, sorry.
No, you're fine. So this is now
that makes sense. Yeah.
Equatorial down. Okay.
Mm-hmm.
Let me get rid of this one. Okay, does that make sense?
Yeah.
Okay, so again, that's how my mind works. I just think if it meets up, the up position is going to be straight. If they meet down, then the down position is going to be more obvious.
Yeah, that's how I think I remember. I just make like 1, 3, 5 will go up and 2, 2, 4, 6 will go down.
Yeah, you could do it that way as well. Yeah, whatever works for you.
Yeah.
As long as you are consistent and it's right every time, good to go.
Okay.
Okay. So have a think about number 2. I'll give you guys about 20 seconds. Try this one. Okay, let's talk about this one. All right. Again, it doesn't matter how you number them as long as you remain consistent. Okay. So at carbon 1, what did you guys draw?
Up.
It's an ethyl group going up. Again, the carbons meet up, so it's going to go directly up. Okay. And at carbon 2, we have what?
axial up, I think.
Okay. So because it's on a dash, this group is
Yeah.
going to be facing down.
Yeah.
Maybe equatorial, right?
So it would be axial down. A tert-butyl that's axial down. You guys see that?
Mm,
Did I confuse you?
no.
No, I just drew mine wrong, so I'm like trying to redo it real quick.
No, you're okay. I'll give you a second. Okay. Is this our most stable form?
No.
No. Okay, so we need to flip it. So we're gonna redraw it like this. Again, my drawings are not beautiful, I apologize. Okay. Carbon 1 is now here. Carbon 2 is here. Okay. Again, it's going to remain up at carbon 1, but it's going to change to equatorial. So it's going to be something like that. Equatorial up. Okay. Because the carbons meet down, so the up position is going to be a little bit, it doesn't look like it's up, but it is. Does that make sense? Okay. And then at carbon 2, it needs to remain down, but it needs to change to equatorial. Okay. So again, it might look a little bit weird, but drawing down kind of looks like that off to the side, right? If it was up, it would be going this way, but it's not. And this is more stable. All right. For sake of time, how are you guys feeling on this topic? It's not anything too crazy, right?
Yeah, no, I feel like.
Okay, let's do number 4 because this is the hardest one that I brought. I can't imagine him doing anything harder than this. So let's try this one. Okay. Give this one a try. Give you just a second.
I have a quick question. It doesn't like start the review or anything, but do you know how the extra credit points are going to transfer to the test from the mock exam?
He adds them to your final exam score.
Okay, wait, so is it like out of 25 though?
I'm not
Like,
sure. It depends on how many you guys have gotten.
Okay. I was like wondering, would it be like 5 points added to 25? Because that's like a generous amount.
Yeah, he is very generous with extra credit because he knows this class is tough.
Oh, okay.
So, and also usually the exams are built, he has like built-in extra credit in them. The exams will be worth out of like 110 points instead of 100, but he only counts 100. So like, for example, you get an automatic 10 points straight out of the gate. So if you got every question right, you could get 110. If you missed 10 points, you'd still get 100%. Does that make sense?
Mm-hmm.
So he usually does that as well on top of the extra credit he gives. So he is very generous that way.
Right.
Okay. All right, well, let's do this one really quickly. So again, I threw a little curveball here with having an oxygen in the ring, okay? But all that's gonna do is just replace one of the carbons with an oxygen like that, okay? Again, we can label this 1, 2, 3, 4, 5, 6, right? So at carbon 2, what's going on?
It's going up.
Yep. Carbon, we got a alcohol group facing up, right? Okay. Carbon 3, alcohol group that's going down. Okay, let's label these as we go. So this is equatorial up. This is equatorial down. Okay, how about number 4?
I have a quick question. So how do you differentiate between like equatorial and axial? Like when you're starting out to draw them, you know what I mean?
Yeah, so like, are you talking, it just looks kind of confusing with this one?
Yeah, so I'm like, how do you know it's like equatorial, not axial starting out?
So all that I do is I look at up and down first. I draw it up and down, and then I determine if it's axial or equatorial. Okay. So for example, equatorial kind of, how I view it is it kind of stays in the same plane as the molecule, right? Whereas axial, it's kind of like going, oh, let's see. It's like, this would be axial, right, on carbon 3.
Yeah.
It's kind of going directly away from the molecule, if that makes sense.
Okay.
Equatorial kind of stays within the same plane. You kind of just have to learn to view them like that. You know, it's just, at carbon 3, axial is going to be straight up, whereas equatorial is off to the side. You can look at it as in the same plane, like at carbon 2, right? This would be axial. Okay.
Yeah,
Because
so
it's going away.
4 like equatorial up.
4 is going to be up. And then because it's up at 4, it's equatorial. So you kind of base it off of up and down first, and then you determine if it's equatorial at that carbon.
Okay.
So your main. Sorry, go ahead.
Anything?
Say that one more time.
I didn't know if there's like any specific rules for like, you know what I mean, like assigning equatorial and axial, or if it's just kind of like an I type thing that you have to look at it.
It is an I type thing. Based on which carbon is attached, because equatorial at carbon 4, right, is different than equatorial at carbon 5. Equatorial at carbon 4 looks like this, right, whereas equatorial at carbon 5, right, looks like that. Equatorial looks like that here. Axial looks like this, axial looks like that. You know what I'm saying? So it's like you kind of, once you determine up and down, you draw it up or down, and then you determine if it's axial or equatorial. Does that answer your question?
Yeah, thank you.
So at carbon 4, this one is equatorial and up. Is that making sense?
Yeah.
Yeah. Now it makes sense.
I made 5 axial down and 6 equatorial up. I don't know if that's right.
Okay, 5 is going to be down for sure. So because the carbons meet up is the more obvious position, what we want to draw it down. Okay, so it's going to go off like this. Okay.
Oh, so it'll be equatorial.
It would be equatorial.
Okay.
And 6 will be equatorial with up.
Yep, perfect. So, so it's going to go off to the side like that, right? But this is equatorial up. Perfect. Does that make sense to both of you? So don't worry about axial equatorial until you have it drawn. Just worry about up and down.
I just have a quick question about the last part. Is it ethyl attached to OH or?
Oh yeah, sorry, I forgot. Yeah, it's just a carbon and then our OH. Yep, and this would still be equatorial up. Yeah, so there's just a carbon in between. Okay, is this our most stable conformation?
Yeah.
Yeah.
Yes, because all of them are equatorial. Perfect. All right, so that's kind of like the hardest one I could see you getting on your exam. Again, just start with up and down, draw it. I guess you're not going to be drawing on the exam, but he'll ask you questions. You know, is this one going to be equatorial up, equatorial down, axial up, axial down, all that good stuff. Okay.
Okay.
All right, I have 4 examples of these converting the other way from the chair conformation to skeletal. Is there one that you guys would like to do together that looks the hardest, or do you want me to just pick one? You want me to just pick one? Let's do number 3. Okay. So these I think are actually easier than going the other way, okay? Because all you have to do is draw your hexagon. I don't know why it went off to the side like that. There we go. Okay. And then we can just label these 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. At carbon 1, we have an OH group going down. Okay. So all we have to do is at carbon 1, draw a dash, OH. Done. Carbon 2, we have an OH going down. All right. Is this making sense?
Yeah.
So what would be at number 3?
Down. No, up.
It'd be no. Wouldn't it be down tert butyl?
Yes, perfect.
Okay.
Down. Okay, because the carbons meet pointing down, so down is it's gonna go directly down is the more obvious position. Okay, if it were up, it would look like this.
All right.
Okay, this is down. Down tert butyl. Okay, at carbon 6, what's there?
I'd say up.
I think it's down.
Okay, the carbons meet up, so this would be up. So it is down. Okay, you guys starting to see the patterns here for like, again, the way I like to look at it is at carbon 6, the carbons meet pointing up. And so the up position is going to be more obvious, whereas the down position kind of goes off to the side. Okay. I know it's kind of hard to get the hang of it, but once you start to see it, it'll make a lot of sense.
Okay.
All right. We okay on that topic? Is that?
Yeah.
All right. All right. Let's move on. All right. So here's Newman projections. Here's our last 4 problems, and let's try to get through all 4 of these because I think this is where you've had the least amount of practice. Do you agree?
Yeah.
Okay. And I'll stay here as long as we need to. If we, I'll give you as much time as you need on this topic. Okay. So convert the following to the most stable Newman projection. All right. So what we're looking at is I drew an eye, which bond we want to look at. Okay. I'll do this first one with you guys, and then you guys can practice the coming ones. Okay. So we know this is our front carbon, and we know this is our back carbon. Okay. So our front carbon is represented with a dot, our back carbon with a circle. Okay. Now, looking at our front carbon, which is right here, okay, where is our hydrogen gonna be? Let's start with that.
Dash is left, is it?
Okay. It depends on which way you're looking at it. We're looking from the right, so if we were to have, basically it's like if you were to take that molecule and turn it and look directly like the eye is looking, okay, the dash is going to the back, so which way is it going to be? Is it going to be to the right or to the left?
I said to the right.
Yep, perfect. So our hydrogen is going to be going off this way. Does that make sense?
Yeah.
So like you're looking at it from the right side, so because the hydrogen's going to the back, if you're to look at it like the eye is looking at it, it would be going to the right.
And then would our little wedged one be going down then for the CH3?
The wedge would be going to the left.
Oh, okay.
Okay. All right, and then the CH3 that's this way would be going down.
Okay.
Okay, let me color code these. So this one is this carbon, okay? Whereas the wedge is this carbon. We cool with that?
Yeah.
Okay. Because all you're doing is it's facing the way it's drawn, right? It looks like that. And so as you look down the way the eye is looking, the wedge in the original is coming towards us. And so when we look the way the eye is looking, it's going to be going to the left towards where we were before, if that helps as well. Okay. So again, now we want to go on to our back carbon. Okay. Where is this hydrogen going to be?
Sorry, which one?
The hydrogen I circled.
Oh,
this
okay.
one right here.
To the left. Or is it facing up?
Yeah, perfect. It's going straight up. Okay. It's all within the same plane. Anything that's not on a dash or a wedge is all in the same plane. Okay. That might confuse you for the second question. Ignore what I just said.
Okay.
Because there is no dashes and wedges, but we can talk about that as when we get to it. Okay, so now we're looking from the right side again. So let's see, which way is this hydrogen going to be facing?
To the left.
Perfect. Yep. So it's going to be going off this way. All right. And how about this hydrogen right here? That's kind of the same color. Let me do this.
So that one goes to the right.
That one goes off to the right. Perfect. We seeing that now, kind of how you draw these.
Mm-hmm.
Okay. And that is the most stable Newman projection because both of the substituents, the CH3s, are on the same carbon, so you can't like rotate one of the carbons to make it more stable. It's any way you rotate it is going to be the same stability. Okay. All right, so let's talk about number 2 here. Okay, so this time we're looking from the left, and if there is no stereochemistry, then you can just choose it. Okay, that's probably how I'll say that. Okay, so for example, this is going to be our front carbon, and this is going to be our back carbon. All right. So again, choose which way you want these methyl groups to face, okay? And just make sure that you remain consistent. So I'll talk through this front one with you guys, and then you guys can do the back one. So we're gonna put this CH3 going directly down, okay? And we'll do this CH3 going off to the right. And then our hidden hydrogen will be to the left. Okay, we chose that. Okay, that's our choice right there. Okay, now you guys work on the back carbon and try to draw the back carbon to make this the most stable Newman projection. Okay, again, I said you can choose it, so just make sure you remain consistent and make, you know, put your bromine where it would be most stable. Give you guys a second to work on it.
So I have a question. So you know how you like kind of want to like set aside since you have a CH3, you kind of want to like keep that distant from like the biggest constituent, but then you also have bromine. So I'm like, which one do you like do? You know what I mean?
Bromine will take precedence over the ethyl group.
Okay, sounds good.
It's bigger than the ethyl group. Yep.
Okay. So I don't know. I put like the bromine to the very left facing down.
Okay, so you said bromine like this. Oh, let's see. Whoops.
Yeah, well.
Right here.
Yeah.
Perfect. Okay, and then where would we want our ethyl group to be then?
I mean, I originally put it down to the right, but I feel like it should be like kind of up, facing up.
Perfect, because going this way, well, let's try it like this.
Well, because it's like the bromine.
Yeah, so it's, you know, no matter what you do, the CH2, CH3 is going to be close to the bromine because they're attached to the same carbon, right?
Yeah.
But the ethyl group here, okay, we want to keep it as far away from these guys as we can as well. So we wouldn't want to put it down here because then it would be in between them, whereas it's only between a CH3 and an H in this position, right?
Mm-hmm.
Okay, and then on this side would be our hidden hydrogen. Does that make sense how you kind of work through that? Okay, so that's our most stable Newman projection. We okay?
Mm-hmm.
Perfect. All right, and I did a horrible job drawing that wedge. That was supposed to be a wedge. Okay. So try this one on your own. I'm not going to give you any hints. See what you can come up with. Let me know when you guys are ready.
I mean, I made one, but I don't know if it's right.
Okay.
Same.
All right. Let's talk about it.
I don't know. I put bromine facing for like on the like the little dot circle one. I put it up to the left.
Okay. Well, let's talk about it. I'm not exactly sure yet. So here's our front and back carbon. Okay. How I would look at this is I would keep all of them in the same position that they already kind of are in. Okay.
Yeah.
So it's kind of drawn like down and then also on a wedge. So the view, I would draw the bromine this way. It doesn't really matter too much as long as you're comfortable with converting it to the most stable afterwards. But I just like to draw it this way because I know, okay, it's down and to the right as the eye sees it. Does that make sense?
Yeah.
Whereas the methyl group is straight up, okay? And then we have a hidden hydrogen going to the back. That's the way I like to think about it. You don't have to do it that way. That just helps me so that I remember what the original was. Okay. And then the same goes for the back carbon. The methyl group is going directly down. Okay. And then we have two hidden hydrogens, and so they'd be going like this. That makes sense? Kind of. Did I confuse you?
Yeah, no, you're good.
Okay.
I just didn't know you could like flip the way your little projection went. I thought it always had to be like essentially a Y, like an upward facing Y for the first one with the dot, and for the one behind it, then it came out the other way. I didn't know you could switch it, so
Yeah, so I mean,
that's good to know.
yeah, no matter what way you have it, right? So these are all in the same plane, right? And then
Yeah.
on this back carbon, the wedge and dash would be facing up. On the front carbon, the wedge and dash would be facing down.
Mm-hmm.
Okay. So again, you can have your eye like this.
Yeah, no, it makes sense, but
Yeah. And so, you know, this would be to the right, down and to the right, down and to the left, straight up. Does that make sense?
Mm-hmm.
Cool. All right. Now, is this our most stable conformation?
I don't know.
Okay. I would say we could have a more stable conformation, okay? Because we could put one of our hydrogens on the back carbon near the bromine. That would be a better choice than our methyl group, okay? So I'm going to rotate 120 degrees this way, our back carbon, okay? So again, our front carbon, 120 degrees. Our front carbon is going to remain exactly the same, okay? We don't want to move the front carbon. But now our back carbon, we moved, basically we're going to shift each of these one to the left or clockwise, okay? So our methyl group will be here now. Our hydrogen 1 will be here. And our hydrogen 2 will be there. Does that make sense?
Mm-hmm.
So now our bromine is surrounded by hydrogens rather than being next to a methyl group, okay? So this is more stable. We cool with that?
Yeah.
Excellent. Okay. So let me draw an eye here. I forgot to draw one. Okay. Give this one a try.
Okay, I made one.
All right.
Mm-hmm.
All right, let's talk about this one. So again, we have our front carbon and our back carbon. Okay. Where did you put the chlorine on the front carbon?
I put it down and to the right.
Perfect.
Yeah.
That's what I would have done. Okay. And how about the ethyl group?
Put it down and to the left.
Okay. You could do that. That's totally acceptable. The way I see it is that it's going up
Put it up.
and that
Yeah.
the hydrogen is going down to the left. Okay.
Yeah.
Ultimately, it doesn't matter too much. Then the back carbon, what did you guys do with the chlorine?
I put up left.
Okay. So that's not right because it's coming towards us. Okay. So it is going to be up, but it's going to be off to the right. Okay. Because it's headed towards us in the original. Does that make sense? It's on a wedge, so we want it coming towards us.
What does actually like coming towards us means? Like,
Okay, because the eye is on this side, right? As you're looking down this bond, okay, it would be going up and to the right, right?
oh, okay.
As you're
Okay.
looking down that bond, the chlorine would be going to the right and up.
I think I can see it. Yeah.
That help now?
Yeah.
You really have to think about this in a 3D way. You have to say, okay, I'm looking directly down that bond. What's going on here? Well, the chlorine is up and to the right. It was originally coming towards us in the drawing, but now it's off to the right because of the way we're looking at it. Does that help?
Mm-hmm. Yeah.
And now we want to determine the most stable, okay? And we can rotate this. Where do you guys think it's going to be most stable?
120 degrees again.
Okay. So what I do, the chlorine is the biggest group. Okay. So what I would do is just basically put the chlorines as far away from each other as possible. So I would rotate at 120 degrees this way.
Mm-hmm.
Okay. So our front carbon, we're going to keep the same. And now our back carbon has Cl there, hydrogen here, CH2, CH3. Let's see, what would that look like if, no, I think that is most stable.
Yeah.
Cool.
So are we supposed to only rotate the back side or?
You could rotate the front or the back. I choose to rotate the back. You can do whatever you want as long as it's the most stable. Yep.
Okay.
I just got used to rotating the back carbon, so that's what I do. Keep it consistent. That's all I'd say. Do it the same way every time. Then you make sure you've got it good. Okay. Any other questions before we finish up?
I think that's it.
Okay. Awesome.
Will the questions be posted like the one that you made just now?
I will post the video. If you'd like me to, I can make a PDF of the questions I did as well. If you want to go back and practice them again, you want me to do that?
Yes, please.
Sure, I can do that.
Thank you.
Okay. I'll get this video and questions posted sometime this afternoon. It takes a while for the video to process, but I'll definitely get that to you guys sometime today.
Thank you.
I mean,
Awesome. You are welcome.
Do you need a recording of it or just like what we did?
I'll actually have the video, so you'll be able to see me drawing and everything.
No, I was talking to him. I was like, because I have everything like written down. I can just send it to him real quick on my iPad. If you want your audio, then yeah, you have to post the video.
Oh, like if you have the like everything written down, like, then it will be great. Yeah.
Yeah, for sure. I can just send it to you. Like it doesn't